Lashi, can you see the screen? Okay, so today I'm going to talk about the in situ S-doping strategy of promoting iron coordinated by nitrogen doped carbon nanosheet for efficient oxygen reduction reaction, or just S-doped iron nitrogen carbon. Today, the content of my presentation, the first part is the overview. The second part is the research content, which include the introduction, the method, and the material used during this study, and the result of the study, and the discussion that they had with the result. And at the end, there is a conclusion. So to start with the overview, in the overview, I'm going to make a simple summary of everything that was done during the study. First, I will talk about the goal of the study. The study was conducted with the goal to improve the transition metal nitrogen carbon as a photocatalyst in the oxygen reduction reaction. The oxygen reduction reaction is used for environmental purpose to reduce the use of fossil fuel, to replace the use of fossil fuel with fuel cell or battery that are more environmental friendly. So this study had the goal to use the metal nitrogen carbon as a catalyst to improve the activity of oxygen reduction reaction. More precisely, they use the in situ doping strategy to enhance or to improve the iron nitrogen carbon activity. And here we can see that it was synthesized through copolymerizing 3 monomers of diacetylene pyridine or DAP. I think during this presentation I'm going to call it DAP because it is shorter and I think less complicated to spell. And the second monomer used was the 3-amterene or TIT, and the third one or last one was the D-tuburia or DTB. And the S-dop iron nitrogen carbon nanosheet with iron coordinated by 4 pyrolytic nitrogen dopant exhibit the highest oxygen reaction reduction activity and stability. This is better than the actual platinum catalyst because today the catalyst that is used for the oxygen reaction reduction is this photocatalysis. It's the platinum based catalyst, but there is some shortcoming with this catalyst and we are going to see it in the next page because this is just a summary. I'm not going into details. So here also is still the summary, and in this part of the summary, this is the summary of the reaction of the whole study because the whole study goal was to produce this one, to produce this nanosheet based carbon. Here we can see at the beginning we have the first element, the 3 first elements that we need. We have the triamethene, the diacetylene pyridine, and the D-tuburia. And here we have salt. So for just an overview, we are going to mix all these 3 elements. This is in situ. In situ means we are going to make mixture of elements. So we are going to make a mixture of this element with the presence of salt. We are going to use different method. One of the method is pyrolysis or leaching using this element. This element is sulfate acid, and we are going to get our catalyst based carbon for the oxygen reduction. So this is a bit of the overview or the summary of what is going to happen or what was done during this study. So this is the research content. The first part of the research content is the introduction. As I said before, today with environmental pollution and other causes of climate change, global warming, the scientists or the researchers are working to use more environmentally friendly or renewable clean power sources. And in this research, they try to enhance, to improve the catalytic activity of mm, the oxygen reduction reaction. Okay, to improve the activity of iron, nitrogen, carbon, recent reports have demonstrated that doping with heteroatoms can induce the redistribution of electrons in carbon networks and tune the electronic structure of the center-tension metal atom, which can further optimize the energy pathway of oxygen reduction, leading to the improvement of iron, nitrogen, carbon. So this one is very important as the introduction because, as I said before, our goal was to use iron, nitrogen, carbon as the catalyst. But today we already have one catalyst. We have a platinum-based catalyst that is used. But this platinum-based catalyst is very difficult to find because platinum is, as the main source element, is difficult, so it is expensive. So today we need one catalyst that is less expensive, that is affordable, so we can use it in more application. That's why we want to build. That's why the study had the goal to build a new catalyst. But this catalyst, just based on iron, nitrogen, carbon, is not enough. Why is not enough? Because there is some shortcoming, and the idea to improve its activity as a catalyst was to do a doping, S doping, and when the S doping was done, the quality or the catalytic activity had a good potential for oxygen reduction activity. Okay, the method and the material used during the study. So different method was used or different methods are used to produce this catalysis. Our iron, nitrogen, carbon catalysis, different methods are used to produce it. So one of the methods is this one, is the one-pot method pyrolysis with the mixture of sulfur, nitrogen, carbon, and iron sources. The second one is the post-treatment as synthesized nitrogen carbon. This means metal via the incorporation of sulfur suspect, the second pyrolysis method. And the third one is the sulfur dope iron nitrogen carbon by pyrolysis. Iron ion ZEF8 to obtain a catalysis iron nitrogen carbon followed by sulfur doping with a secondary pyrolysis treatment using D-urea as the S sources. The problem is it is difficult, as they say here, it is more challenging to incorporate the doping. The S doping is more challenging than the incorporation of nitrogen due to its larger atom size and lower electronegativity, limiting the understanding of the role of the sulfide doping in metal nitrogen carbon. Therefore, it is highly desirable to develop a precise synthesis of sulfide dope metal nitrogen carbon via molecular level design. So during the study, this is the method that the researchers are going to use to produce the catalysis, because these three methods that I mentioned before have many shortcomings. Okay, this is the same image as before, but with different role or different use. And here we are going to talk about, because as I said, okay, method and material. So here I talk about the method used. So here I'm going to talk about the material. Material are different. I did not mention all of them here because there's a lot, but some of them, the hydrogen of course is going to be used, nitrogen, sulfur. Out here, as I said before, we have salt and iron, oxygen, carbon, and our three main base source element for this study. Okay, and there is the experimental part, that this one is the result and the study directly, and the first part is the synthesis and the physical characterization of iron nitrogen carbon sulfide nanosheet. So as you can see, these two images may look like, but the second one is more precise. There's more details. So the synthesis, because there's two parts, the synthesis and the physical characterization. First, I'm going to talk about the synthesis. The synthesis of iron nitrogen carbon sulfide nanosheet has three steps. The first step is the ball mill mixing. The second one is the incorporation of ferrous chloride. The third one is pyrolysis, and there is also the leaching with acid sulfuric. But the ball mill mixing and the ferrous chloride incorporation are almost at the same time, because so here we have our first element. Our first element is 3